On today's episode of the Ag Irrigation Collective, we're going to visit about subsurface drip irrigation. Stick around. Hi, I'm Wes Schaefer, your host with the Ag Irrigation Collective. Sure do appreciate you stopping by today and join us for a podcast. We're going to take a look at a white paper that was put out by the University of Nebraska, Lincoln, from their Irrigation Engineering Division. And this white paper discusses and goes through some advantages and disadvantages of subsurface drip irrigation. I know there's been a lot of discussion lately regarding subsurface and surface drip irrigation, and I thought it was important that we go over it and learn a little bit about it with each other so we can all be more well-informed if this is some form of irrigation that may function properly and be beneficial on your operation and your irrigation practices, because there are some nuances regarding subsurface drip irrigation and some expense that some folks are unaware of. So I wanted to cover that today. So what is subsurface drip irrigation? And within the industry, I guess if you'd call it that, it is referred to as SDI, which also surface drip irrigation, which is what you see a lot in vegetable, human consumable type of crops. I don't necessarily know what surface drip irrigation is referred to if subsurface is considered SDI. So SDI, or subsurface drip irrigation, basically applies water directly to the root zone using a buried polyethylene tubing. It's also known as drip line, dripper line, or drip tape. Drip lines come in varying diameters and thicknesses in order to maintain acceptable irrigation uniformity for your different field lengths. Smaller diameter drip lines are used when short lateral lengths are required. As lateral length increases, a larger diameter drip line must be selected in order to maintain adequate irrigation uniformity, and that's for some friction loss type of scenarios. The thickness of the drip line wall is directly related to its durability, of course. Drip lines with small thicknesses are mainly used for temporary installations and can be discarded after a short time, such as when being used to irrigate high-value crops. Thicker drip lines are used for permanent installations, and thicker drip lines can be also able to withstand higher operating pressures of the water. And the cost of the drip line, of course, is directly related to both diameter and thickness. Small holes that are located in the drip line are called emitters, and they're usually spaced anywhere between 8 and 24 inches along the length of that drip line. During the irrigation, pressure forces water out of the emitters drop by drop. And once the water is in the soil, its movement and wetting pattern depend on the physical characteristics of the soil. In a fine textured soil, for instance, which when you lean more toward clay, that is considered fine textured soil, water tends to move laterally and upward compared to sandy soil, which is a coarse soil, where water tends to move mainly downward. The amount of water that can be delivered through a drip system depends on the drip line diameter and spacing, emitter spacing and operating pressure, emitter size, and emitter design. A variety of drip lines are now available from different manufacturers to fit the specific design requirements in your different soils and crops and, of course, weather conditions. Some advantages of subsurface drip irrigation are your water application efficiency. So subsurface drip over other irrigation methods is that it has a potential to be the most efficient irrigation method available today. The word potential, though, is stressed because irrigation efficiency not only depends on the irrigation system itself, but also on its proper design, installation, and management. If designed, installed, and managed correctly, can subsurface drip be more efficient than any other irrigation system? I think it can be, but there are a ton of variables that go into that. Since drip lines are usually installed in the soil between every other crop row, the system only wets a fraction of the soil volume compared to other systems. This does leave space in the soil to store water from rainfall, and it may reduce the net irrigation requirements of that soil. Also, since drip lines are buried about 13 to 18 inches below the soil surface in corn, the soil surface stays dry, giving somewhat of an illusion as you're looking at your field. A dry soil surface means that practically no irrigation water is lost due to evaporation or runoff. If the system is managed correctly, deep percolation losses due to irrigation can be eliminated. The only small inevitable water losses are those needed for flushing the drip lines and filtering the system. Therefore, in subsurface drip system, it can deliver water with efficiency of 95% or higher, so long as that is maintained properly. This means that for every inch of water that is pumped, 95 1/100ths of an inch or more stays in the crop root zone where it is needed. And because of the potential high irrigation efficiency that can be obtained with subsurface drip, it may be a good alternative for areas where irrigation water is limited. It should be noted, however, that although water savings is an important consideration, it should not be the only factor to consider when selecting an irrigation system. So your potential water savings, as we just referenced, researchers in Kansas have reported that net irrigation needs could be reduced by 25% with subsurface drip irrigation while maintaining high corn yields. Net irrigation needed, however, does not take into account system inefficiencies. The actual water savings that can be achieved with SDI depends on the irrigation efficiency of the system with which SDI is being compared. For instance, let's say the producer is switching to subsurface drip from furrow irrigation. Although it is difficult to know the average irrigation efficiency for a furrow system, but we're going to assume the efficiency is 65%. It can be more or less depending on your management, soil type, and other factors. And in a previous podcast, we discussed some surge irrigation that is used within furrow irrigation, and I believe we did discuss there that it's higher than a 65% when used under that method. If the net seasonal irrigation requirement for corn is 15 inches, and you take into account water inputs from rainfall and residual soil moisture, approximately 23 inches of water will be needed to be applied through furrow irrigation to meet the crop needs. And if you consider a 95% efficiency for subsurface drip, only 16 inches of water needs to be applied using SDI. So that's a difference of about 7 inches of water that can be saved at a farm level by using SDI instead of furrows. From a watershed perspective, no water is actually saved by using SDI. Water that is consumed through evaporation may go to reduce the transpiration needs of the crop, and water leaves the field as runoff or deep percolation can be reused downstream. From the producer's point of view, pumping has been reduced by 7 inches and pumping cost by approximately 1/3. In this case, SDI also has environmental benefit, since the water that is applied in excess to the net irrigation requirements using the surface irrigation system has a potential to create environmental problems such as nutrient leaching, soil erosion, and pollution of surface and groundwater sources. So if we compare SDI to a center pivot, the water savings may not be as significant as it is for furrow irrigation. For instance, given a similar situation of corn grown under a center pivot with net irrigation requirement of 15 inches, and assuming the center pivot has an irrigation efficiency of 85% to satisfy the net irrigation requirements of 15 inches, the producer then will need to apply 17.6 inches of water, as opposed to the SDI would still be backed by 7 inches within the furrow system. So there are some also potential yield increases. SDI can be automated to allow frequent water applications. It also can be used to frequently inject fertilizers and other chemicals such as acids, chlorine, and even pesticides with the irrigation water. Subsurface drip systems are often managed to apply small amounts of water and other inputs daily or even several times a day. Small and frequent applications can be adjusted to match the water nutrient needs of the crop. Typically, when you spoon feed water and nutrients, it can result in increased yields and decreased nutrient losses. The magnitude of the yield increase can be obtained using subsurface drip, and it's still an open question for row crops such as corn. However, a recent study in Texas compared SDI and sprinkler systems for grain sorghum. The researchers found that under deficit irrigation, subsurface drip irrigation resulted in higher yields, while under full irrigation, there is no yield increase. Significant yield increases, however, have had long been documented for SDI in several vegetable crops. And I think mainly where those increases have been seen is because subsurface drip irrigation is more prevalent and more frequent in those vegetable crops or high-value crops. The labor requirements required for subsurface drip is after the system is installed, the manual labor required to operate the system is similar to that to operate a center pivot. Much less than that required for a surface system. Subsurface system also lends itself to automation, which of course can considerably reduce your labor. However, and I think we'll get into this in the disadvantages portion of our podcast here, there is to install subsurface drip is quite laborious. So your underground system, when you have the irrigation underground and keeping the soil surface dry, in addition to reducing evaporation, it allows farm equipment to enter the field even during irrigation events. In arid areas, a dry soil surface can also reduce the potential for weed germination and restrict growth of shallow-rooted weeds. A dry soil surface also limits crusting of the soil surface, which can be a problem with other types of irrigation systems, and we do see that with sprinkling as well as very heavily with flood. Because the drip lines are underground, high wind speeds do not affect irrigation uniformity and efficiency, as they will do with sprinkling systems. High winds can significantly damage center pivots, but it will not affect the SDI systems. Having the system permanently installed underground, starting irrigation early in the growing season without losing considerable amount of water due to the high evaporation rates usually occur under bare soil conditions. And depending on the system capacity and water availability, it might be necessary to start irrigating early in the season to refill a dry soil profile. That's why also it's important to charge your soil in the fall if you have excess water in the fall time, so you start with a less dry soil profile. Starting with an empty soil profile may not allow low-capacity systems to keep up with crop water demand during the growing season, especially during peak water use periods. Because drip lines are underground, subsurface drip could be an alternative method for disposing of wastewaters, especially those with an unpleasant smell that do not adapt well to applications using other methods. Although more research is needed, in order for this to happen, research at Kansas State University have successfully used SDI to apply livestock wastewater from cattle feedlot lagoons. I am interested to see that study from Kansas State because that would take an awful lot of filtration and different methods to get that water clean enough to run through the subsurface drip. So your field size, shape, and terrain is a factor as well, but some advantages here. SDI adapts well to fields of any size and shape. However, it does not work well with rolling terrain because of the pressure differential in your drip lines, causing non-uniform water applications. Although uniformity can be increased using pressure compensating emitters, the additional cost may not be feasible for low-value crops. There is some potential energy savings in subsurface drip. They operate at relatively low pressure and deliver small flow rates. Emitters usually require a pressure of 4 to 15 psi and deliver flow rates of 16/100ths to 1 gallon per hour. Because of the low flow rate requirements, SDI can be operated with smaller pumps than will be required for, say, a center pivot or furrow systems, which may be an important consideration in places with low-yielding wells. Because of these characteristics, some researchers have reported significant energy savings by shifting surface irrigation to drip. It should be noted also that lower capacities and energy savings are only possible because of higher efficiencies with subsurface drip compared with other systems. The energy used by a pumping system depends on a combination of factors including your flow rate, pumping depth, pressure at the pump, time of operation, and pumping plant efficiency. How these factors are combined in a pumping system, of course, determine if energy is actually saved with subsurface drip. A surface system, for example, will require less pressure and less operating time than subsurface, although it may require higher flow rates. SDI may require less flow rate, but the pump will have to be operated for a longer time to be able to meet the crop water requirements. At the end, if less water is pumped with SDI due to a significantly higher efficiency and improved water management compared with other systems, it is possible to save energy, although it may not occur in all situations. Even though subsurface drip irrigation emitters operate under low pressure, the pumping system should supply enough pressure to account for other pressure losses within the system. And within this document, there is some tables and some photographs that are pretty neat. So as you click in through the video and podcast description here, you will be able to click into this link and take a look at this PDF that I'll have attached here. Typical pressure losses in the different components of a well-designed SDI system reported by researchers in California. Also, by evaluating hundreds of micro-irrigation systems, including SDI, they found that about half of the systems operated with less than 35 psi at the pump, and the other half required higher pressures. So that's pretty good to be able to keep your pump pressure down in order to be able to make that work. So we're going to now dive into some of the disadvantages of subsurface drip irrigation, and they are about equally as many as the advantages. So the initial investment cost. One of the main disadvantages of subsurface drip is its high initial investment cost. SDI systems are expensive compared to other irrigation systems. The cost per acre varies widely depending on field size, shape, and location of the water source and level of automation that you desire. Researchers in Texas estimate the investment cost for different irrigation systems. And in this table, the chart, the net cost takes into account all the allowed tax deductions based on two tax categories and present value of those deductions applied over a period of several years according to the tax regulations. So this table shows that under a conventional furrow, the cost per acre is $165, and then after net, you're down to $142 with conventional furrow irrigation per acre. A center pivot, the cost per acre after net is $252 per acre, and SDI after net is $570 per acre, thereby doubling what a center pivot costs to operate and nearly 4x of what conventional furrow costs to operate. In Nebraska, an average gross cost of between $500 and $800 per acre is a good estimate. This includes the cost of installation, which usually about $200 per acre. Depending on the location of the water source, a higher investment may be required to convert pivot corners to SDI, meaning all of your infrastructure and pipe in the ground that you will be needing to put in place in order to make this function. Economic comparisons between center pivots and SDI done by Kansas State University are what is in this chart. However, they have shown that fields get smaller with SDI and it becomes more cost effective. In their analysis, however, they did not include the dry land alternative, considering the dry land alternative is important because in some situations, it may be economical or more economical to not irrigate at all. Now, I'll tell you, in dry land, when I think of dry land, I think of either nothing growing at all, because I am in the desert state of Utah, or in the northern part of Utah, dry land can grow safflowers, hard red winter wheat, some barley varieties where there's no irrigation whatsoever. However, we do in those northern areas of dry land do rely heavily on a very good heavy snowfall in the wintertime. And so dry land, though, in, say, eastern Nebraska is totally different than dry land in the western United States. And so it'd be interesting to see kind of what they're talking about, that it may be more economical to not irrigate at all, of what type of fields they're referring to here. So determining the economic break-even point between SDI and center pivots, however, is complicated since the analysis is very sensitive to the expected crop prices, value of the water saved, expected yield increases with SDI, field size, and the life expectancy of the SDI system. One thing I want to mention about the expected yield increases is there are so many outside factors beyond just irrigation that we can even have a natural weather event that may be odd in 1 year or over several years that can cause some major yield increase or decrease differences that it's, in my opinion, it's very difficult to gauge just based on your irrigation system. And some of these factors are very uncertain. For example, the life of an SDI system is not known, meaning do you need to replace this drip tape or drip tubing every 5 years? No, I don't think there's been much study on that, and I don't know that some of these systems are old enough, or these large systems are old enough to know how long they're going to be in place. Of course, the longer the life of the system, the more economic sense it makes. System evaluations conducted by the Irrigation Training and Research Center in California showed that system performance, as indicated by measured distribution and uniformity, was not related to the age of the system. They found 20-year-old systems with excellent performance. The life expectancy would depend a great deal on how well a system is designed, installed, and maintained. So in general, center pivots make more economic sense for large areas, and SDI could be a good alternative for small, odd-shaped fields, especially when irrigation water is limited. Government cost-share programs may make SDI more economically viable as the need to save water increases and as concerns about the environmental impacts of irrigation become more important. So another disadvantage here that we're going to get into is water supply and system capacity. As stated above, one of the advantages of SDI is that water and nutrients can be applied frequently and in small amounts. For growers obtaining water from an irrigation district, the water delivery schedule may not be flexible enough to take advantage of this system attribute. That is a good thought, because I know there's a lot of systems where you're on a water turn, and some guys even pumping out of deep wells are on a turn setup in order so they don't deplete that aquifer from the neighbors. In cases In these cases, a water storage tank or reservoir may be required, which will increase the cost of the system. In order to take full advantage of SDI, it is assumed that a constant supply of irrigation water is available. It can be problematic for farmers depending on water delivered from a canal system in a rotation schedule. Under this situation, irrigating early in the growing season to refill a dry soil profile as needed with some low-capacity systems may not be possible. Another limitation to water supply, even for farmers pumping groundwater, can be the interruption in pumping imposed by load control for electric power systems. This is aggravated by the fact that load control is usually imposed during the peak water use periods when crops need irrigation the most. It's also important to point out that SDI systems are usually designed for frequent applications of small depths of water. In systems with low capacities, producers cannot afford to get behind in the irrigation. Since they will not be able to catch up and will not be able to meet crop water requirements, especially during periods of high water demands. So that's a big deal when you do get behind and you can't catch up. So there is those challenges there. One other thing that I don't think it mentions in this article is when you are germinating crops, in most cases, there is a secondary either flood or sprinkle irrigation required in order to germinate those crops, and that is another disadvantage to subsurface drip irrigation, is the requirement of a secondary system in order to germinate those crops. And in also other circumstances where salts in the soil are high and you need to drive those salts in the soil down, where the small amounts of the subsurface drip water are ineffective in achieving that, there is a secondary system needed. So there can be a real disadvantage there. So time management requirements for SDI can be higher than for other irrigation systems, especially the first couple of years when the learning curve is steep. This is because operating a subsurface drip system requires special periodic maintenance operations such as chlorination and acid injection, which are not required for other systems. So the acid injection, just so you're aware, is necessary using acids such as N-furic acid in order to keep your emitters from being clogged from water deposits, hard water deposits. And also applying fertilizers and other chemicals using SDI requires special care and knowledge. So the limited drip line lengths is also a disadvantage. In order to maintain high uniformity with subsurface drip line lengths have to be limited. The maximum drip line length is a function of the drip line diameter, emitter flow rate, slope of the land, and emitter spacing. For this reason, large fields may need to be divided into smaller units or irrigation zones, which may imply additional cost for main lines and submains. With current products, the maximum drip line length is limited to approximately a half a mile. So if you're out here irrigating, even if you try doing, say, a 640-acre piece, which is a mile by a mile, and which is one section of land, you end up needing to split that field up into multiple different sections to accommodate, thereby giving your underground infrastructure far more money than, you get these smaller pieces that are, say, on pivot corners and things of that nature. The installation of an SDI system requires specialized equipment. It is labor intensive and represents a significant portion of the initial cost of the system. Soon after the installation, water needs to be run through the drip lines to detect leaks and to open the flow path through the soil to the full extent of the tape diameter. Otherwise, soil may consolidate around and collapse the drip lines, which could restrict water flow. For producers who receive water from a canal system, water may not be available in early spring and late fall when SDI systems are usually installed. So you do need to consider when you install SDI if you have water available so you can run through these systems. Although SDI systems are relatively easy to install in the rockless soils commonly found in, say, Nebraska and other high plains states, installing SDI systems in rocky soils, which are common in other places, could be difficult, if not impossible. So your soil type and how much type of rocky soil you end up with and that you have in your farming operation, it may not be necessarily possible at all. So the inflexible design also is a disadvantage. Aside from the cost, it is critical that SDI systems be properly designed, installed, operated, and maintained. During the design phase, decisions have to be made that cannot be reversed after installation. Decisions like drip line diameter, drip line length, emitter diameter and spacing, drip line spacing and depth, main line diameter, type of filtration and injection systems, all of that need to be made by both the farmer and the irrigation system designer. This is quite important since SDI systems are less forgiving of design errors than other systems. And the recovery value of an abandoned SDI system is very low, meaning if you go and try and remove it, you're pretty much out that drip tape if it was installed improperly, if it was not sized properly. Working with an experienced SDI designer certainly is a good investment. The producer should consider that once a system is installed, it cannot be easily changed. For instance, the installed system will have fixed drip line spacing and depth, which may limit the types of crops that now can be grown and the type of tillage practice that has to be used or cannot be used in order to not tear up your system. Your emitter clogging is also another issue. One of the main problems with SDI and other types of drip irrigation systems is emitter clogging. It is a good idea to perform a water quality test before designing your system. You need to be aware of potential problems that may influence the system design, performance, and maintenance needs. Water quality tests for SDI systems include parameters that are not commonly measured in standard water quality tests for irrigation. Your water quality tests for SDI need to include bacteria population, total dissolved solids, total suspended solids, water hardness, and concentration of hydrogen sulfide, iron, and manganese. Proper maintenance is absolutely necessary for SDI systems to be successful. Since the emitters have very small diameters, they can be clogged by very small particles. This makes it absolutely necessary to keep those particles out of the system. Once the emitters are clogged, it may be difficult to unclog them, and depending on the nature of the problem, several types of particles, including soil particles, chemical particles, and biological particles, can clog emitters. Clogging by soil particles is avoided by proper filtration and flushing. The filtration system should be considered the most crucial part of your SDI system and should be carefully selected during the design stage. Now, I've seen filter systems for subsurface drip get very expensive depending on your water quality and water dirtiness coming in, the cleanliness of your water that's on its way in. It can be very costly. Chemical precipitates such as calcium carbonate can develop inside the drip lines when the pH of the water is high. To avoid the formation of chemical precipitates, acid is usually injected in the irrigation water to lower its pH. You also end up with biological particles like algae and bacteria slime, on the other hand, are usually prevented by a chlorine injection. And also to kill bacteria, it is useful, which can live in iron, manganese, and sulfur. You also might need to periodically shock chlorinate the well. Although the proper filtration system will keep most soil particles out of the system, some particles will still pass through the filter and settle inside of your drip lines. These very small particles need to be eliminated by periodically flushing your system. Therefore, it is extremely important that the proper flushing systems is included in the design. And that usually includes connecting the drip lines to a common PVC flush line that's installed at the bottom end of the field. Crop roots growing around drip lines can also plug your emitters, especially when the soil around the drip line is dry. Those roots will make an effort to find the water. This phenomenon is commonly known as root intrusion. Keeping the soil around the drip line sufficiently wet and injecting chemical products to kill those roots are management practices commonly used to alleviate this problem. When water in the drip line is drained after irrigation, a negative pressure can be created inside the drip lines. Under this negative pressure, soil particles from outside the drip lines can be sucked into the emitters. And of course, this problem can be avoided by installing air and vacuum release valves, which allow air into the system at strategic points and not allowing that vacuum to suck that soil back into those emitters. Rodents, of course, can be a problem with subsurface drip irrigation. And they are one of the main problems that limit the successful use of subsurface drip to irrigate your row crops. And this has been noted in Nebraska. Some rodents, such as gophers and field mice, like to chew on the drip lines, and it can be a major problem. Evidence of a leak can be detected by field inspection and by measuring pressure drops and high flow rates in the system. Locating and fixing leaks by rodents is a difficult task since it requires digging to expose the tape. Rodents can create single leaks or may create multiple closely spaced leaks that may run distances of 10 to 15 feet or longer. To avoid these problems, the potential for rodent problems in the area should be evaluated prior to installation, and if needed, a rodent control and prevention program should be implemented. So I also want to note that a rodent control and prevention program certainly would be beneficial under any irrigation practice. The benefit of, say, flood irrigation is those rodents are drowned out if they are in existence. Under pivot, we see rodent problems more frequently, and they are then need to be controlled. But if you're able to control them on any scenario there, if you control rodents, they typically will have higher crop yields under any irrigation scenario. So your rodent control program should include not only your SDI field, but also the surrounding area to keep rodents from moving into the SDI field. And currently there are no clear guidelines on how to solve this problem fully. However, rodent problems seem to be more severe under dry conditions. Therefore, keeping the soil surrounding the drip line wet seems to alleviate the problem for the most part. And of course, others recommend applying certain chemicals to either kill or repel rodents. And as we get in more those rodents, we're going to visit deeply about rodents in a future podcast across all irrigation types and crop health of how they can be damaging to any crop system and why that is detrimental. So as I touched briefly earlier about seed germination, since the underground SDI system keeps the soil surface dry, seed germination may be a problem, and early growth can be limited by water stress. This is especially true in sandy soils, where little water moves upward in the soil profile. The depth of installation of the drip lines also influences how close to the surface the water can move. In arid areas, a backup irrigation system may be needed to promote seed germination. So that's a big deal if you need additional seed germination because of the depth of your subsurface drip irrigation. There are several other disadvantages that are listed within this document that you can reference to this. That's about the end of the document there that we're going to conclude with. We've gotten a little long in the tooth here on the podcast, and I appreciate your willingness to hang out with us today and plug us in while you're puttering around in the tractor or doing whatever you're doing while you're listening to the podcast. If you find value in these Irrigation Collective podcasts, I sure appreciate you sharing it around to your friends. And also, if there's some benefit to you and you think that future episodes can be beneficial, we appreciate it if you'd subscribe to the YouTube channel or follow us on Spotify or Apple Podcasts or wherever you're consuming this material. And I hope you can find it beneficial in some of this that you're learning about. So we do appreciate you stopping by. Be profitable, my friends, and we'll catch you on down the road.